everyone for coming. Like I said, I know there's a lot of things going on campus, and really appreciate that you took the time to come to the second event we're organizing this semester. Uh, the first event we organized was Professor David Vernon, whom Russell thinks of as Superman. And Vernon did a good job at taking us through what it means to do research. So we want to move on a little bit from there to talk to someone who is doing research, to see the work they do. And we also want to go a little bit to the edge to see something that is on the fringes of a field that many of us are passionate about, so to speak. I would introduce Russell a little bit, and then I would give him the floor and he would start. So just to let you know, I've had the privilege of meeting Russell in person. So if you want to see someone who knows a celebrity, you know that I know a celebrity. Okay, so Russell has an associate's degree in mechanical engineering from École Normale Supérieure Polytechnique Yaoundé, 2017. And then he went on to obtain a bachelor's degree in computer science from the University of the People in 2019. Another bachelor's degree in science and technology from AIX Marcel University in 2019 as well. And then he proceeded to complete a master's degree in scientific computing and mathematics of information from the University of Strasbourg in 2021. At the moment, Russell is a PhD student at the University of Bristol, and the title of this PhD project is Scaling and Error Quantification of Data-Driven Fluid Simulation Techniques for Human Interaction Tasks. If you have time, please Google a little bit about Russell and the work he does. I think it's really encouraging that for most of us who maybe think that Africans are doing just applied research, it's good to see one of us doing a lot of basic research. So thank you very much, Russell, for taking the time to talk to us. And the format of our meeting is going to be, we are going to have Russell present for 45 minutes or more if he needs. And then after that, we are going to have a question and answer session. We are hoping that the meeting would not be above 1 hour. And then please know that we're recording the meeting for the benefit of those who would not be able to attend. So thank you, Russell, and over to you.
Oh, no, thank you for that introduction. It's really I hope I can live up to what you just said. Actually, it's really impressive. As from what I got, this crowd is mostly familiar with machine learning, or is it graph machine learning in particular?
I would say machine learning, not graph machine learning.
Okay, so I'll be showing some new stuff, I guess. Is that, yeah. So just let me figure out how to share the screen here, because I'm not okay. Yeah, it was the it was the big green button that I was avoiding. Can everyone see my slides? Let me put on full screen. Can everyone see the slides?
Yes, we can.
Oh, okay then. I guess I'll start now. As you can see, the title is graph neural networks. It's I want to put it graph machine learning, but it's essentially, I'm going to be focusing so much on graph neural networks in this talk that it just made sense that to just have the title as graph neural networks. But that said, I'm going to be covering some techniques that are more general in terms of just graphs in general. So we're going to be covering some techniques, but before covering the techniques and the application of it, I just need to say, need to give a shout out to these are my supervisors. These are the people that made this happen. Yeah, I'm funded by the UKRI, and I'm mandatory. It's mandatory. I am required to put them in every slide, in every talk that I do. So here I am doing that. So I'm going to start a bit with the motivation behind graph neural networks, and then before going into the techniques and the foundation and the types of GNNs that are out there, and some of the connections that we have with transformers actually. And then the third part of the talk is going to be more about a specific application of it. What like Empon was saying before, like I don't know if it's on the fringe of research, it's at it's the state of the art, but it's definitely something that we've been doing and really passionate about sharing this. So graph neural networks, what's the motivation? First of all, it's graphs are everywhere in nature. We have them, it's everywhere, so it just makes sense to represent data as graphs and then do some learning on them. So we can represent molecules, mass spring, damper systems, for example. The B one that we see here, for example, these enable us, for example, to do tasks like simulation, the mass spring damper system, which is something I've done a bit. So I kind of like this representation, this usage of graphs and sentences, path trees, and seeing graphs like this. So lots of applications, lots of graphs in nature. And also what we normally don't think of as graphs can be represented so, like images, just the connectivity. So just imagine a cell connected to a neighbor, and then that makes an edge. But the language of graphs, I'm going to cover that later in this talk, so it's not that important. I'm not going to focus on the technicalities or the edges and nodes and the appellations for now. And also texts can be represented like graphs, and there's actually a really fun anecdote about this. Hello, I think I heard, like, is that a question or?
Sorry, that was not a question. I think someone was joining.
Oh, okay. Oh, okay, interesting. So I'll just keep on then. But also I would argue the most important motivation behind using graphs is the inductive bias that they bring. So inductive bias essentially just means like what kind of bias can you bring to your model to prioritize a solution over another? For example, we all know the Bayesian rules here, and this is the kind of inductive bias we want. So if you have a good inductive bias, it can lead to very efficient solutions to your neural network, or when I say model here, I mean like anything that can enable learning, essentially. Now, I mean, I think I'll cover some examples for it to be more clear. So in fully connected neural networks, as we can see here, there's not much inductive bias, but then you go to convolutional neural networks and you have the notion of sharing weights, where you have this spatial inductive bias. So the same weights, the same kernels is used at different places on the same image. So that is some kind of inductive bias. And with recurrent neural networks, you have this spatial inductive bias that you're bringing, the sequentiality of it all. And graph neural networks, they bring this kind of inductive bias in the sense that you can have as much inductive bias as you want. So it depends on the features of your edges, how connected is your graph, if you want more inductive bias, you just have more representative features. And this is one of the biggest motivation behind graph neural networks, because they enable you to have as little or as much inductive bias as you want in your model. And I just want to do like a quick segue here with geometric deep learning, because it's an attempt to actually unify all the fields of deep learning. I don't know if many of you guys are familiar with geometric deep learning, but it's a step towards general AI. And it kind of builds on this notion of having priors. It's like invariance, meaning that if your output doesn't change much. Equivariance means that your output changes the same way as the input, and then all sorts of invariants that I'm going to generalize and just call them symmetries for now. I'm going to clarify all of that a bit later. And the way I tend to think about geometric deep learning is that you kind of split your domain into three separate sets, essentially. So you're trying to predict, for example, you get the signal 3 here. So you have 3, but what is the domain on which you're learning? Are you learning on a graph? Are you learning on an Euclidean domain? So how is your underlying domain is, and what kind of symmetries does that domain enable you to have? In this case, for example, we have like a clear grid here, and it would be good if this grid is symmetry invariance, like shift invariant. So if the number 3 is shifted a bit from the right or from the left, or to the left, I mean, would the prediction, would the hypothesis class, the F here, the function in the hypothesis class, would the model predict the same value? Would the model predict that you still have a 3? And this is actually one big problem, because you can look here, like when these invariances are not guarantees, it can lead to like serious problems. Like if I ask you here, is this a rabbit or is this a duck? I think the humans are kind of confused. It's not easy. It kind of depends. Everyone has their own inductive bias built in their minds, I would say. And so does the machine, so does machine learning models. You can see here the prediction kind of depends on the rotation of the picture. And this is kind of what it means to be non-rotation invariant. And as opposed to what we want is some kind of invariance and some kinds of equivariance. So no matter how you shift, you keep getting the same prediction, you keep getting the same output, or the output changes the same way. So yeah, this is what I'm kind of meaning by symmetry preserving. Geometric deep learning is a field that just like tries to unify all this, try to perform learning on domains that have these symmetries. It can be a graph, it can be like an Euclidean data, it can be all sorts of domain essentially. And I think this picture here just like generalizes everything. For perceptrons, I think most of us are familiar with perceptrons, for example. So they only require your function to be regular, for example. So if your function is regular, then yeah, you keep getting the same. So these are, the way I'll put it is that these are universal function approximators. So they are deterministic in that sense, whereas CNNs are translation invariant due to the fact that they share their weights. And graph neural networks, which are the focus of our topic today, I would say, these are permutation invariant. So if you number your nodes differently, does that actually change the prediction, the output of your models? And we want that to happen. It's not always the case, but that's something that we want to enforce. And fun fact, actually, perceptrons, which have been used, they are so famous, like these multi-layer perceptrons, but we know that these are universal approximators, but these are not translation invariant. These are not shift invariants like convolutional networks are. So this is one of the reasons in the 70s, people were using perceptrons to do AI, but it was failing, but people didn't know why. And this is one of the reasons. These are not shift invariant. They needed something more. They needed these convolutional neural networks, for example, that came with the revolution we all know AI had in the past decade. So we're going to focus on graphs, and I'm going to cover a bit of like foundations, what's going on in the graph neural networks. So here, usually I like to just like pause if someone has like questions for the first part, but is that okay, Lemfron, or should I just wait to the last till the end and then
I think you can go on to the end and then we take questions. I think
you
that's
take questions at the end? Okay. So I'm going to start with just like covering some of the terms that we're going to be having. So for example, vertices of a graph. I think most of us are all familiar with vertices. I'm going to say nodes sometimes, but it's all the same thing. Edges, and then there's a feature that is not usually used when talking about graphs. It's the global feature U. So yeah, this is just like something that represents the whole graph. It's a feature, an attribute for the whole graph in itself. You can think of if you have like a molecule, which can be represented as a graph. So is this molecule, does it have a particular property? Does it smell good or does it smell bad? Or you can think of it like that. Whereas edges and node vertices and node attributes V and E, those are kind of particular to what your to the edges and the nodes. And also, lots of tasks can be performed. So you can have like a node level tasks. So you can just predict the property of a node. You can predict the property of an edge, or you can predict like you can have like a graph level prediction too. So I just wanted to mention this because like I'm gonna be, yeah, I might be using these terms a lot in the next minutes. And there are a few challenges when doing learning on graphs. So when the graph is large, up to this day, it's actually a challenge as to how to actually split the graph, or how do you do learning on a large graph? Because if you're splitting the graph and you're training it, say you're splitting the graph and making it a strong scaling problem. So you're splitting the graph into multiple parts and then just training it on different node or cores or GPUs, I would say. How do they communicate with each other? It's like that's a challenge today. And there's the dynamic graphs, for example. How do you, if a graph is changing as you're learning? So you can look at this, the scene graph here. You can have like watching. So the connection, what if the edges change as the graph is evolving essentially? And also adjacency matrices, which are mostly used when doing learning on graphs. These are not necessarily permutation invariant. So if you renumber the nodes differently, you get a different adjacency matrix. And if you do the learning using that adjacency matrix, you're not guaranteed to obtain the same result. Now, luckily, if you use adjacency list, the ordering doesn't matter here. So it can actually solve your problem, but it's another problem of its own. But for today, we're gonna go through like the like just like basic graph neural networks first, and then we're gonna complicate things by the end, I guess. And by the time we complicate, our graphs would be permutation invariant. So when you're doing a prediction with a graph neural network, it's essentially just like a series of transformation you're doing. You can see these graph neural network blocks. So you get an input, a graph, and then your features, which, as I was saying before, can be either edges features or node features, or can be also global features. So at each step, you're kind of applying some sort of transformation to those attributes and then changing them to get your transform graph, and then doing some classification. You just apply a classification layer there, like a sigmoid, like we normally do with other machine learning paradigms, the learning paradigms on Euclidean data. Now, lots of blocks you can apply like successive transformations on these. And there's a danger not to apply too many transformations. So it's actually like a really interesting problem in graph machine learning at the moment, where if you keep applying too many transformations, your graph tend should just be all the same. It's like the features just tend to be the same. It's like a diffusion problem. So they call it the over-smoothing issue in graph neural networks. So you need to apply like lots of graph neural network blocks, but not too many, in such a way that you're not gonna have the same features or on all the edges or on all the nodes. Now, what goes into a node? What goes into a graph neural network block? Sorry, what goes into a block? So you can apply a transformation on the global features independently, like with the function f here. You just take the u, you apply the f, and then you get a un plus 1. You can do the same thing for v, and you can do the same thing for e. So these are not connected to each other. The functions are not communicating. So in order to predict the next attributes for the nodes, you're only using the previous attributes for the nodes. You're not using the edges. You're not using the global features. But it is possible to actually combine those in such a way that your elements, your graph elements, communicate with each other. It's not easy for sure, but that's the way graph neural networks learn best. So this is what is presented here. So if you're trying to predict the next set of attributes for the nodes, you could use a pooling function on the edges and then combine those to get some proper attributes. So yeah, we're gonna cover now a few techniques, and then the first assumption we're gonna make is that the graph is small, static, unweighted, and undirected, because it makes things really easy. And when things are like this, we can use the adjacency matrix, and it's not gonna matter most. Obviously, as I said before, the adjacency matrix come with its own set of issues, let's say. So in this formula here, A is the adjacency matrix I mentioned, and then H is the attributes for the vertices, and then W is the learnable parameters. So in this case, for example, it's just a dense layer. So essentially you have your edge, your node attributes in H, you're multiplying those by the adjacency matrix, and then you're multiplying it again by a learnable parameter W, and then you're applying a nonlinear function like a sigmoid or like the usual functions to obtain the new set of node attributes, which we call H prime here. And essentially what you're doing, if you look closely, is that you're kind of just averaging the neighborhood information in every node. So every node has, that's because that's the information that adjacency matrix gives you. If two nodes are connected, you get 1, and then if two nodes are not connected, you get 0. So it feels like the graph neural network, this simple, very basic one, is just aggregating information from the neighborhood node, and then the W parameter is kind of saying, how do you aggregate that? What does one neighbor matter more than the other, for example? But this also, it comes with its own issues, because with the adjacency matrix, for example, there's not the notion of self-connection. So if is a node connected to itself, because as I said, the graph is undirected here, it's unweighted. So we tend to use this A tilde matrix here, but it just adds the identity matrix to A in such a way that the graph is going to be, and a node is going to be connected to itself. So when you're computing the new attributes or the new features for this edge, you need to consider the old features for this edge again. So don't just use the neighbors, also use the previous values for this particular edge. And sometimes it's important to do some kind of normalization, because when we're just multiplying the matrix as we're doing in A here, we're just adding stuff. Matrix multiplication is essentially an addition of stuff. And then when you're adding, things can blow up. Imagine if you have like many layers, many blocks, so you just keep adding and then they can blow up. So it's important to normalize, and usually we normalize with using the degree matrix. So the degree matrix is just, it's a matrix that just gives you the degree or the number of neighbors that each node has. So you're kind of, this is like a proper averaging now. And then the way we normalize to, it's important to do some kind of symmetric normalization. So you don't just divide by the degree. You divide by, you raise the degree matrix to the power of -½ and then -½ again. So it's kind of a symmetric normalization, which tends to work best. So this is the original description of the graph neural network, which was presented at ICLR 2017 by Keith and Welling. Really famous paper that I really advise everyone to have a look at that paper. Really fun. So this is the very basic concept of a graph convolutional network. But what we were describing so far, this was all about node attributes, right? Because we were just changing H and H prime, those were node attributes, multiplying them by the adjacency matrix. But we can actually incorporate edge features too with this notion of message passing neural network. I'm pretty sure like this is also a very famous architecture. I'm sure like lots of people have heard about this. In this paradigm, the thing is, a node, when you have a node and you consider its neighbors, each neighbor computes a sort of message that they send to the node, as you can see in this picture. So a message, what is in a message? A message for an edge. For an edge, a message can be, what is the source node? What is the ending node? What is the edge attribute itself? So you need to figure out a way to combine, as you can see with this message function on the right here. So the message from node I to J is FE is the message that computes these, and then you use the origin of the edge, and then you use the endpoint of the edge, and then you also use the edge attribute itself. Now, how do you actually combine this? Because the node attributes can have like a huge feature space. It can be like, I don't know, 3 features, just say 3, not that huge, yeah? And then the edge features can be of a different dimension. So how do you combine a vector of size 3 and then a vector of size 2? Not even considering that there are not as many of those. So it's not always easy to know how to combine these. Usually a concatenation is the best you can do. You just like concatenate, just like have 3. So you just concatenate the source edges, the source node, HI, and then you concatenate that to HJ, and then you concatenate that to EIJ. You don't really care about the dimension of each in this case. Usually that's the best you can do. And then obviously you need like a readout function that when you have all these messages going to a node I, when you have all these messages going to a node I, how do you combine them now? And also you're using the attributes, the node attributes for that node I. So how do you combine all the messages from the neighbors J into the node I, and also using the attributes for node I itself? So that's what we usually call the readout function. So in this case, you can leave it also, as I was saying, how do you combine all this? You can leave that to a MLP usually, just like a small multi-layer perceptron can do this job really efficiently. Now, the complication is usually how do you combine those features, because these are just inputs to the MLP. The way you combine it is the beauty of the graph neural network. That's mostly what's gonna like differentiate your model from another one's model, which is doing essentially the same thing. So it's something to be very wary of. So yeah, this is so now there's this paradigm also of graph attention network, which is a bit different from what I've been talking about so far. So far we've seen a very basic, I would say, a very basic graph neural network, where we're just multiplying the features by W, by some learnable parameters W. And then we also saw in the previous slide that we could use like machine multi-layer perceptrons just to learn these message functions and then these readout functions to form this this message passing neural network, which is also really famous. It came out like 5 years ago, Gilmer al. So also really famous paper. I also want to point out in this slide that when you're computing the messages, so your node of interest is the one in red, and then the neighbors are the ones that you can see circled in this blue square here. Now, when you're computing the messages and then sending them to the node in red, it kind of feels like it's just an averaging neighborhood information. So it feels a bit like you're doing a convolution. So this is like what you would do on a grid, and this is what you're doing on a graph. There's some similarity in what you're doing, which is kind of the reason these are all some sort of convolution, essentially. So yeah, I just wanted to point that out, that yeah, it helps to view these as convolutions, because that's what they are. Whether we call it message passing neural network or we call it graph convolutional network, there's also a term called I forgot the term, but there are so many terms. But essentially what we're doing is just averaging neighborhood information and then bringing that. Now, sure, with normal CNNs, I would say, you have that weight sharing that you're adding to, which you don't have here. I mean, weight sharing in the kernel of the convolution, you don't have that here, which makes things a bit different, but definitely worth considering. So transformers, these are really revolutionary. These have been revolutionary in natural language processing, and they can be applied to graphs. So it's the same ideas from transformers can be applied. So the message passing is powerful, but as we saw, you have to manipulate the edge messages. So how do you combine them, especially if their feature space is different, or their size is different from the size of the vertex of the node features? So if they were all the same size, I don't know, three features, then you could add them, you could multiply them, you could do lots of stuff. But when they are different size, you have to manually manipulate them. You have to think about concatenating them. And if you concatenate them, how do you extract the information you want afterwards? So you have to keep that in mind. So it's expensive in that sense. And it's also expensive because, yeah, it's computationally expensive having to compute for every node messages, information from all the neighbors. And yeah, that's why they are only applicable to small graphs normally. And it is actually to solve that kind of problem that the graph attention network was created. So in the previous slide, we saw that these were essentially just averaging neighborhood information. But what does one node matter more than the other, for example? We don't know that. So in this graph attention network, the coefficient, essentially the alpha ij, is what the network predicts. The network predicts these alpha ij coefficients, of course, added to the dense, to the W. These are still learnable parameters that we're going to add afterwards, after the graph attention step. So we learn these alpha ijs, and then we kind of normalize them during the with a softmax like formula. Essentially, no, we learned Aij and then we normalized them in order to obtain the alpha ij that we use to essentially as the readout function in this case. So this is the concept behind graph attention network. So don't compute everything explicitly by hand, just do things implicitly. You learn the coefficients implicitly. So I attached this screenshot to the paper. This is 2018. Essentially, really famous names here. I think you recognize like Yoshua Benjo and Peter. These are really famous people, and yeah, really fun paper to read too. Now in practice too, the alpha ij's coefficient, you actually need to compute like lots of them, not just one coefficient. You compute like 3 of them just to mimic the process of attention in transformers. You compute 3 in the sense that do you view this edge, or do you view this node, do you view it as a query now, or are you viewing it as a key? I don't know how familiar you guys are with transformers, but that's usually how they work. You can view an element as a key, in which case you need to average the information about near it, essentially. But with text, where transformers are mostly used for natural language processing. So if you're focusing on a particular word, what are the other words in the sentence that are more related to that word, or for the task that you're doing? So you're trying to answer a question. So if one word is the key of the question, is the heart of the question that you're asking, what is the answer? What is the answer? What word is the answer? And the coefficient for that answer word is going to be, of course, bigger than the ones for the other words. And so that is if you're viewing that word as a key, but you can also view a word as a queue, as a query, and in which case its weights are different, essentially. So it actually leads to what I was trying to mention here. So when you're trying to view graphs as transformers, there's some really nice parallels, even in the way things are computed. And the way I usually like to think about it, because like this guy wrote like a really nice article in The Guardian, and the way I like to think about it is that the bridge, the connecting part of it, is to view like a sentence. You view your sentence as a graph, but rather than having a sequential, rather than having like a sequential graph, like a sentence, like first word, second word, third word, you actually have like all your words connected to each other. And then your graph attention network is going to determine which words are important for which other word, essentially. So that's like, I think this concept is really unifying. It generalizes everything. And that's the way I think I like to generalize things. I like to unify theories. I don't know how I'm doing with time. So am I doing fine with this? So I think I still have like,
so good.
Yeah, I still have like 10 minutes to the.
Yeah, let's give you 15.
Okay, yeah. Because this is actually the application part of it, the one where I was I'm really looking forward to show you guys this. So this is the work we did trying to apply graph neural networks to simulations, accelerating simulations. So first of all, simulations are very important, especially high fidelity ones, for weather forecasts and for computational fluid dynamics. Our goal was to actually simulate a gas turbine during operation, and to be able to do that to the point, to such high fidelity that you could actually validate the model without ever building it. So certify the model, I would say, yeah. So in order to do that, you need some computational power. You need some some high performance computing clusters. And when we see the trends in parallel computing and serial computing in the past decades, I would say, you can see that the computational frequency has been plateaued. It has stagnated for a while. So if we cannot get enough power, if we are like kind of suffering for the computational power, the thing I would say to fix this is to actually build better algorithms to make better use of what we already have. And that was the motivation behind this project that we did. So when you're performing fluid simulations, big fluid simulations, you end up with big linear systems at the end that you have to solve. So AX equals B, X is our unknown, and B is known, and A is the matrix. This is the problem here. A is extremely large and it's extremely sparse, as we can see one example on the right here. This essentially what you don't see, the yellow elements, those are just zeros. So this matrix is extremely sparse, and we want a machine learning algorithm. We need to solve the system by taking advantage of that. Right now, there are direct methods that you can just invert the matrix A, of course, but the cost of doing that is big O of n cubed, which is don't even try it, because you can see here, you have like, you can see on this plot, I think it's really small, but you can have like 3 million degrees of freedom in this matrix. Just imagine cubing that. You can also have iterative methods that just, you start with a guess for x0 for a solution, and then you iteratively solve the system until you get to a good enough guess. Now, these methods can be easily parallelizable to make better use of the clusters that we have. Good smoothing properties, but they tend to be unstable due to low frequency, and they tend to be slow to converge too. So it's still a big O of n cube. So multi-grid methods are kind of state-of-the-art methods that tend to perform way better than all of these. And we're trying to improve on these multi-grid methods. What do I mean by multi-grid method? Essentially, when you're trying to solve a system AX equals B, you're solving the system. Just imagine you're on a grid. Imagine the grid is defined essentially by your matrix. The matrix A defines a grid for you. So the bigger your matrix A, the bigger the grid that you have. And the multi-grid idea is to restrict that domain, restrict that grid, and then solve the system, try and reduce that problem onto a smaller grid, onto a coarser grid. And then you just restrict, and then when you've solved and then you've obtained the quantities that you want on the smaller grid, you can bring them up again. And then you can call this step prolongation. You can bring those quantities back up again. And then you use those prolongated quantities to correct for the guess that you have, because multi-grid is a sort of iterative method. The fact that you see here that the one that we go down with a bump here and then we go up with a different thing, because the quantity that is restricted is not the same as a quantity that is prolongated. And the reason we do this is because when you're solving on a really fine grid, that is good into reducing low frequency, but not high frequency. So if you want to reduce high frequency errors, you go on a coarser grid, because it's just gonna dump everything out. And then you restrict till your problem gets small enough for you to handle. So mathematically, I think this translates to this. You start with your X star is your exact solution, and your error is E. Your error at step n is En. And your current approximation is Xn. And the thing that multi-grid assumes is that En is your error is composed of an oscillatory part and a smooth part. Oscillatory part means it's really high frequency, and then smooth, really low frequency. So the first step is like you generate your meshes, you set up an initial guess, and then you do like a pre-smoothing step. So you smooth out, you kill out the auxiliary part of your error, because like the goal is to get the error to 0. And as I said before, if you're solving on a fine grid, then you're killing out the high frequency component of the error. You're killing out that component. And then how do you do that? When the term smoothing is a bit, it can be confusing, but you use like a normal iterative solver. It can be like a Jacobi, it can be a Gauss-Seidel. You use a normal solver, like a normal iterative method. And then you just do like 1, 2, or 3 steps. And then you will kill out the auxiliary part. Now, when you've killed the auxiliary part of your errors, you're still left with the smooth part. The beauty of it is that if something is smooth, then you don't need a fine grid to approximate that quantity by it, because that quantity is smooth. So that's actually one of the reasons you go on a coarser grid. You go on a coarser grid to approximate the smooth component of the error. And then if you're on a coarser grid, then that smooth component, it was smooth on a fine grid, but it becomes a bit oscillatory. It becomes a bit high frequency on the coarser grid. And then you have to repeat the step again. You have to repeat the procedure, the multi-grid procedure, to smooth out again. So yeah, so that's a bit how it goes. You transfer the fine grid residual to the coarse grid. This is the restriction. I highlighted it in red because this is where the machine learning is going to come into action. So step 5 and then step 7, which is the opposite, the prolongation of it, prolongate the error back onto the fine grid. So we started by restricting the residual, and then now we are prolongating the error. So we're prolongating a different quantity. It's not the same, but the prolongation and the restriction operator are linked. One is the transposed of the other, which makes things very simple. So our network will only have to deal with one operator, either P or either R. Essentially, we call it, we deal with P because of the rectangular shape it has. It has more rows than columns, and we kind of prefer that. So the essential quantity in this case is the error propagation matrix. So from one step to the other, how do you multiply? How does the error increase or decrease? Essentially, you multiply that by a matrix M, and you want that matrix to be as small as possible. What does it mean for a matrix to be small? Essentially, you want the eigenvalues of that matrix to be as small as possible. So, so you want the spectral radius, which quantifies those eigenvalues. You want that quantity to be as little as possible. What I was describing so far is actually called geometric multigrid, but we are dealing with algebraic multigrid here, AMJ. I'm going to be using this term a lot, so just wanted to put it out there. And yeah, AMG it's not really important to know the difference for this talk, but so it doesn't require a grid, whereas JMG requires a grid, but it definitely does the same thing. So not that much worry. And I wanted to iterate to press on the fact that M is the error propagation matrix, and it's the thing that we want to make as little as possible, because if M is small, then your error doesn't propagate from iteration to iteration. Now, I should point out that there's been previous work on this, and A has to be symmetric and positive semi-definite, which has big restrictions, which means you cannot just use any method to handle these. Now, there has been previous work on this, but all of them have their own setbacks, which I won't elaborate on them that long. Now we need a robust method. We need a method that works on all kinds of grid, large and sparse matrices, and it's also cheap. So that's the goal I kind of mentioned earlier. Now the machine learning side of it, people have tried using machine learning for this problem. Now, previous work, I think it started like 3 years ago. So their solution only worked on structured grades, like the one we see here. But we want something that works on unstructured grades. There's also been actually some work on unstructured grade, but it didn't work. So it was kind of our predecessors in this job. So we kind of took over from them and tried to make it work. So how do you make something work on something that worked on structured grade, make it work on unstructured grades like this? When I say this is like we're solving the fluid simulation on this kind of grade. So your matrix A is not as nice as the one you would get from this. That's the complication that it brings. So I think this is the pipeline, the learning pipeline that we do. So in our case, we start with a random matrix A. We generate it randomly because we're only doing training now. But the end goal is to have A that actually comes from a fluid simulation, from a jet engine simulation. The first step is to do some pre-processing. So we extract. So we first of all know which nodes are going to be coarse and which nodes are going to be fine. So we kind of extract a coarser grade from the original fine grade, which was defined by the matrix. And then we feed all of that to a graph neural network. And then the graph neural network predicts how the prolongation, it predicts the prolongation operator. So in the processing, we knew that the fine grade was made of these nodes, and then the coarse grade was made of this subset of node, But how do these connect to each other? So if I want to compute the quantity on a fine grade, how do I average the quantities on the coarse grade in order to prolongate? It's an interpolation problem. So the role of the GNN is to predict those weights, those prolongation weight, those interpolation weight for P. And then when we get P, the matrix P, the prolongation operator, we use that to compute the matrix M, the error propagation matrix. As we can see in the formula here, P appears a bunch of times. And then we evaluate the loss function on M. The goal is to make M as small as possible by reducing its eigenvalues, making its eigenvalues really small. But eigenvalues are kind of unstable with neural networks. So the spectral decomposition of a matrix it's a known problem. So we avoided that by actually working with the Frobenius norm, which is a surrogate metric, but it bounds the eigenvalue from above. So if we are minimizing the Frobenius norm, we're also minimizing the eigenvalues. And then we're also adding a few physics-informed loss functions, like the normalizing. We want the sum of all the row elements in the matrix P in the prolongation operator. We want the sum of those to be equal to 1 because you're interpolating. If you're interpolating, then the sum of the weights of what you're interpolating from should be equal to 1. And then there's also a penalization. You're penalizing if the weights are negative, because we all know that weights must be positive. So you kind of enforce that into the loss function. You bake that in. You tell the graph neural network to kind of not do that, essentially, and do so. This is a soft. These are kind of soft constraint that we're giving to the network. And after we evaluate the loss function, we use the autograd, the automatic differentiation, the backpropagation process to improve on the weights of the neural network. So the MLPs I kept mentioning earlier. So this is where we improve on them. And maybe I can just mention a bit what the graph neural network in this case is actually. So first of all, the matrix A. So you have like an example of a matrix A here. And then when you have a matrix A, the first thing, as I said, pre-processing, you extract the sparsity pattern. So we had it's a 7 by 7 matrix, but we only want 4 of them to be part of a course node, of a course grid. So fine grid has 7 by 7, but the course one is 3 by 3. And then what the network is going to do is going to predict the prolongation operator P. So which will be a matrix of size 7 by 3. So how do these nodes connect to each other? Essentially, how do you prolongate? How do you interpolate if you have the values on the course grid? How do you bring them up on the finer grid? So that's what the network does. And the architecture of the network itself is when you give it a graph, or essentially when you give it a matrix, A, which is a graph, you can view it as the adjacency matrix of a certain graph. And then that graph, we build that graph, and then we feed that graph to the network. The first thing we do is first of all, we deal with the edges and the node features independently. So we have like a MLP to kind of encode the information in the edges and the node features independently, and we only connect them during the message passing layer. So the core, the process, the 3 steps here that you see. So this is where we kind of use a proper message passing neural network to actually use information from both nodes and both edges to improve, essentially, to do the learning process. And then when we've done that, we need to decode that information into something that looks like a prolongation operator. So a prolongation operator has its own peculiarities that you need to consider. So you need to decode all of these features into just single values. So just scalars, essentially, one scalar per edge. And some scalars have to be equal to 0 because of this. So that's a bit, so this is called an encode process decode architecture, and we implemented that in the DGL. So DGL is for Deep Graph Library, and it uses multiple backends. It has like PyTorch and TensorFlow. You can have like as many backends as you want. So the tools that we used, I mentioned DGL already, MATLAB, NumPy, of course, and PyTorch, AMG. So we did all of this and built everything on AWS CloudFormation, which I recommend. Like everyone should actually try and use AWS when your machine learning problem gets out of hand, because like Google Colab is they are not that I don't know if they're not happy giving free compute anymore or something like that. They have so many restrictions lately, and well, not just lately, but it's been going for a while. But if you kind of want to do some learning intensive activities, then AWS is one of the places to go. Yes, and we can see here how the loss functions decrease on both the evaluation and the training sets. I just want to point really quickly that DGL is a really nice graph learning library, and they have all these convolutional layers, graph convolutional layers implemented. So you can just pick one and then put it into your network. Of course, you need to worry about how are my edges, how many features does my edges have, how many features does my nodes have. So you need to worry about that, of course. But what they do nicely is that they give you the information on how are those connected, or how they use that information in order to build new attributes. So for example, the graph sage layer here, or the sage convolution here, they tell you exactly how they are using the edge features, because in our problem here, the edge features are the most important ones. If you have a matrix A, like the matrix A I kept showing earlier, the entries in that matrix are actually edge attributes. So those are the most important attributes that we have. So I recommend this library, especially if you're used to using PyTorch. There's also PyTorch geometry, which is nice. I've never used it, but I've heard good things about it. And if you're a JAX user, so the new JAX, the new kit around the block, so I would recommend Giraffe. It's really nice. But if you're really used to TensorFlow, I'm not sure I can recommend any library for if you're trying to do some learning on graphs, because I don't know why, but they just keep all the good libraries are deprecated. So they had GraphNet for a while, they have SONet for a while, they have even Haiku for a while, and it just got, they just left the project. So most of the developers are now working on JAX. So I don't know, maybe that's one of the reasons their projects you just keep leaving projects behind. So I cannot recommend a proper library for doing graphs if you're only used to TensorFlow. I would say JAX is not that different. It is conceptually, but the architecture, the resources you use from the ground up are essentially the same, the XLA and all that. Yes, I just wanted to mention that, and then just finish with some of the results that we got. So when we did that, we got about 27% improvement by using an AI to actually learn the prolongation operator for the multi-grid method, rather than doing it by hand, because you can compute the prolongation operator by hand, but that is, first of all, it is slow, and then and then it can be terrible. So these are some of the results that we get. We think we can do better. First, we need to eliminate the sources of noise, and then what we've been trying to do lately is to integrate machine learning deeper and deeper into the simulation process. So not just at the end when you're trying to solve the linear system, but when you're doing the simulation itself. Sadly, I won't have enough time to present that work today, but maybe on another opportunity I'll do that. So as a take-home message, I would say AMG is a state-of-the-art method for solving a linear system. You can use AI or specifically graph neural networks to accelerate that. And we need more researchers on this. So if you guys are tempted to kind of come, we are welcoming. So please do. So in the long run, these are kind of the things that we're planning on doing. And you can follow the projects that we have on GitHub for updates. This is the project I mentioned that I won't have enough time today to talk about that. That said, thank you very much for listening. Thank you so much. If you have any question, I'll be the time.
Thank you very much, Russo. That was very much of a whirlwind. We said that this was going to be research on the fringes, and it is really research on the fringes. I really admire the amount of work you have put into preparing this talk and the depth of the work you have done as well. Like Russell said, we'll be taking questions now. So if you have any questions, please just unmute and then ask your question. Okay. While other people are thinking about their questions, Russell, I have a question for you. Bringing back everything from the very technical talk we've just had to more sort of like over like, let me say, high level talk.
Overarching.
You did mention graphs as encoding bias, right? And I think it's kind of implicit in their structure with the relationships. So my question to you is, how's that going in terms of, maybe in terms of simulations in the context in which you've spoken of your work, that's not something to really fear, but in terms of maybe encoding bias that is like representative of our human biases and stuff like that, how do you think that positions graph learning as an approach for the future in which bias is a very important topic?
That's a really nice question. I mentioned this part. I didn't have to put it in here, but because I really believe bias is the thing that is going to save machine learning. Really, it's like, it's important whether it's for humans and whether it's for machine or whether it's for anything. And the most important thing about the bias or the inductive bias is that it saves us so much time. whatever information you can bake in your model, like please do. If you know that you want your solution to be like to be a certain way, you have to put that you have to encode that information somehow in the neural network, right? And if you do that, first of all, it saves you like tons of time in terms of training, because HPC facilities, they are out there, but they are not infinite. They are slowing down, and we need to think about how we use them more carefully. And yeah, if you have information about your network, whether it's convolutional, whether it's the inductive bias, as I said, like with graphs, if you have like a graph that you know is a structure preserving, what kind of symmetries you have, please bake that in. And one of the easiest ways actually to do that is with the loss function. Like I mentioned, like the physics inform loss function, for example. Like in our case, we knew that the weights of the prolongation operator, they all have to be positive. So we don't have to let the network predict anything. If the network predicts something that's negative, you penalize it. You give it, like you add that to the loss function rather than decrease it, something like that. So you add the negative of that to the loss function. So those kind of information, first of all, they save you like tons of times in terms of training your network. And also they just make your solution a bit more explainable, in the sense that, like, I'm in a CDT. I think I mentioned that earlier a bit. So a CDT is like a center for doctoral training, and the overarching idea behind our CDT here in Bristol is to build AI system that can better help humans. I think it connects a bit with your question in the sense that how does the human trust the AI? How do you make the AI be trusted by the human? And one of the things you do that is by having some kind of explainability in what the AI does. If you just use a neural network, you don't know exactly what the weights in the neural network mean, do you? We don't know that. But if you add into that some form of bias, some form of penalization, like a soft penalization in the loss function, you know that you can sort of explain, you know that your answer is not like this. For example, you have some extra information in terms of explainability. I think that's the idea I'm trying to present here. And the physics of your system essentially is important, just as all sorts of inductive biases, whether it's the graph, whether it's the Euclidean data, and that. So thank you very much for that question. I hope I was able to just like answer a bit and give you more clarity into it.
I think you did give a wonderful answer to the question. I really liked the dimension on which you went out according to bias and explainability. I think that's a very good way to look at it too. Two more questions for you before I see if other people have questions. The first question is, you made mention of the fact that we need to have these kind of approaches to machine learning going deeper into the simulations, not like, yeah. Do you want to touch more on that? How do you see that playing out? And then the second question would be, are there any relationships between graph machine learning and quantum learning, quantum machine learning? Any relationship between that?
Thank you for those again. I think I'll start with the first one. You mentioned, can you repeat again? Because like the first one was about.
So you mentioned that you'd like to see this kind of approaches to machine learning going deeper into simulations instead of maybe solving the systems of linear equations, right?
Yeah.
But how do you see that playing out?
Oh, actually, that's what I'm trying to do now, actually. So using machine learning in the simulation, not just at the very final step. In this case, one easy way, one basic way would be to use a physics-informed neural network. So you have your simulation. You don't build a system to simulate that. You just give an AI, and the AI predicts the result for you. essentially it's the easy way, I would say, but it's also difficult because it is so data hungry. You have to feed so much data to the model for it to understand what you want it to say. So what you want it to do, I would say, in that scenario. So that's one way of using AI in the simulation. The problem with that way is that the solutions, they tend to not be as accurate as you would want them to be. So just a slight perturbation gives you, the network is just confused in so many ways. So you can go that route, just say, yeah, I want easy implementation, but I'm happy to lose accuracy. That's one way of doing it. Another way is to kind of combine the two in there's this new framework of differentiable simulations, in the sense that you're not actually using a neural network to do things, but you're just using the same principles that the neural network uses, the kind of back propagation algorithm. You're using the back propagation algorithm to do everything by hand. So you make your simulation differentiable, just like a neural network is, I would say. Like a neural network is essentially a series of operations. Yeah, you do a convolution, you do I don't know, you multiply the weights by a certain matrix, the inputs, you add a bias in there. So the series of operations in neural network are all differentiable, and that's how we're able to back propagate through them and improve on the weights of the network. Now, you can also do that with your simulation. So you say you're simulating fluids and you're using a technique like finite volume method. So you can make your method differentiable. You just need to write it you just use the proper libraries like JAX, which is like a composable differentiable framework. You use JAX, and then all your operations are differentiable, and you can back propagate through the entire simulation, just like you would do with a neural network. And that's one robust approach actually to do learning. It's just picking up now. It just came out like 3 years ago, back in 2019, and it's in everything. So that's one way. In doing that, you kind of have the robustness of you don't have to lose accuracy anymore. Whether you're doing an optimization process, whether you're doing you have the robustness of it, but it's also extremely complicated. So it's always a balance. Building a simulator from scratch and making sure that it is differentiable, it's not an easy task, especially if you already had a good simulator back there. So it's not. So it's always a balance, I would say. You can either choose accuracy over ease of use, or the other way around. Yeah, as to the second question, you mentioned quantum machine learning? Yeah, I must say I'm not exactly an expert in that. I'm barely an expert on graphs. I've been doing it just for a few months, but I don't really know. I've read about quantum computing. I've heard the fact that the three things that you want nowadays in terms of research or advanced research, or if you want funding for something, for example, AI for sure, quantum computing next, and then you have some sort of crypto just to add to that, and then you're sure you're going to get funding. So yeah, that's one thing. So when you say graph machine learning, quantum machine learning, you're kind of combining the two hype domains. And yeah, it feels like it's something that we should know something about, but I'm not sure. I really don't know much about quantum. Sorry.
Thank you very much. Any other questions? Okay, it doesn't seem that a couple of questions I asked you were questions people sent to me via private message.
Oh, thank you for answering those. They were really entertaining questions. Really pushed my brain to actually think about.
But then just for the last question, just before we go, we're way over time. So I think a couple of people have been dropping off. Last question before we go.
Yeah.
You did mention that you've only worked on graphs for a couple of months. So
Yeah.
what advice will you give those of us who are looking at this as an option? Because it seems really dense. What do you think gave you the background to be able to move into it so fast? What advice will you give us
Um,
as we start out our machine learning careers?
yeah, I mean, my part wasn't that I took over from someone. That's the thing. Like
Uh,
someone was actually doing it and it wasn't working. And then I came and actually it was easy for me in that sense. Now, if you want to go about graphs from scratch, I would say the idea is always identify your problem nicely and make sure graphs is the thing that you need in that scenario. Yeah. Yeah, identify your problem and then it all goes from the application area, I would say, because as you said, the domain is it's dense and there's so much research going on graphs in general. So there's so many flavors of graph convolution, but what can we actually use those for? I think that's one big problem. If you can, you know the problem you're trying to solve, and then you actually improve on, you actually use graphs or the kind of graph that would actually suit your problem. I think that's the way to go.
Okay. Thank you very much, Russo, for your time. I really appreciate that you took off time. Busy Friday, you should be resting, but then you took the chance to speak to us. We're really grateful for your talk, and I can assure you that when we're going to be choosing the classes we take next semester, we would have this talk and what we have seen in mind. And from me and everybody that is a member of the leadership of the Research Club, as well as all the members of the club, thank you very much for your time.
Thank you to you. Thank you. And very, very good work moving forward. I look forward to see what you guys do next. Okay.
Thank you very much. Thank you, everybody, for coming. Have a great evening.
Yeah. Have a great evening, guys. Bye.